When we think of chemical solutions, our minds default to liquids. We picture colorful fluids swirling in a beaker, merging until perfectly clear. But chemically, a solution is any homogeneous mixture of two or more pure substances, where the composition can be varied within specific limits. Every solution is built around two foundational actors, the solvent and the solute. The solvent is the component present in the largest quantity. The solute comprises any and all other components present in that mixture. This ratio establishes a strict rule. The physical state of the solvent dictates the final physical state of the entire solution. To accurately model these systems, we have to look past the assumption that solutions only happen in liquids. We must map the interactions across all states of matter: gases, liquids, and solids. Because matter exists in three primary states, every solution can be categorized by the specific phase intersection of its solute and solvent. We can map these out on a simple 3x3 grid to view all possible configurations. In gaseous solutions, the solvent is a gas. The mixture of oxygen and nitrogen in the air we breathe is a gas in gas solution. When a liquid acts as the solvent, we find configurations like gas in liquid. Oxygen dissolved in water is a precise example, and it is the mechanism that sustains aquatic life. The most counterintuitive category involves solid solvents. Solid solvents can dissolve other solids. Copper dissolved in gold to create alloys falls into this category. Even though an alloy is a solid piece of metal, its constituent atoms are distributed uniformly. It is a genuine homogeneous mixture. Multiplying 3 solvent states by 3 solute states yields exactly 9 distinct types of binary solutions. Memorizing these 9 specific combinations is a requirement for advanced chemistry exams. Classifying a mixture within this phase matrix is the mandatory first step before applying mathematical models or quantifying concentration. Once the physical state is established, we require precise metrics to express exactly how much solute is present. Mass percentage is the mass of the component divided by the total mass of the solution. Because it relies on a fixed mass ratio, it is used in industrial applications, such as commercial bleaching solutions. For liquid and liquid mixtures, we use volume percentage. A 35% volume mixture of ethylene glycol is the ratio used as antifreeze to lower the freezing point in car engines. When a solute is present in trace quantities, we switch to parts per million, multiplying the ratio by 10 to the 6th power. To see the precision of that scale, 1.5 parts per million of fluoride prevents tooth decay, and just 5.8 parts per million of dissolved oxygen sustains life in seawater. This formula represents mole fraction, the foundational metric for thermodynamics. You derive this ratio by dividing the moles of one component by the total moles in the system. Because you are dividing moles by moles, the units cancel out, leaving an entirely dimensionless ratio. This creates a mathematical rule. The sum of all mole fractions in any given system will always equal exactly 1. These static formulas are effective for measuring fixed physical states, but they lack the dimension of temperature, a gap we have to address for laboratory work. Molarity is the most widely used concentration unit in lab settings, but it carries a specific limitation. Consider these equations. On the left, molarity equals moles of solute divided by liters of solution. On the right, molality equals moles of solute divided by kilograms of solvent. Volume expands and contracts with temperature changes, while mass remains an absolute constant. Heating a solution increases its total volume. Because liters are the denominator, the measured molarity changes, even if no actual solute is added or removed. Conversely, measuring by the mass of the solvent ensures that molality remains immune to this thermal expansion. This is a strict rule for board exams. Never use molarity for colligative property calculations where temperatures fluctuate. Molality is mandatory. Choosing a concentration metric is a thermodynamic problem. It requires matching the mathematical tool to the physical vulnerabilities of the experiment. Reaching these concentrations requires us to understand solubility as a physical limit. The golden rule of dissolution is strict. Like dissolves like. Polar solutes require polar solvents, and nonpolar solutes require nonpolar solvents. This equation loop demonstrates that particles entering a solution do not follow a one-way street. It is a continuous two-way process. Dissolution, where particles enter the solvent, is in constant competition with crystallization, where particles collide and separate back out of the solution. A saturated solution represents the exact point of dynamic equilibrium. It is the moment where dissolution and crystallization occur at identical, canceling rates. Thermodynamics firmly dictates this physical limit. In an endothermic process, the dissolution visibly absorbs ambient heat from its surroundings. If that process is endothermic, increasing the temperature provides more energy, forcing the solubility limit higher. Solubility is not a static endpoint. It is an active balancing act governed by molecular polarity and thermal energy. When a solid crystal finally dissolves into a completely clear liquid, the physical mixing process has reached absolute equilibrium. The required workflow is clear. First, define the solution's physical state using the 3x3 phase matrix, and then establish the exact solute to solvent ratio. If the system will experience heat fluctuations, selecting a temperature-independent metric like molarity is the next step. These rules of mass, volume, and temperature apply universally, from the trace oxygen dissolved in the ocean to solid copper in gold. Establishing these exact quantities is the prerequisite for predicting complex physical behaviors, like vapor pressure under Raoult's law. Recognizing solutions as rigorous, quantifiable thermodynamic systems is the foundation of advanced physical chemistry.